This is the 10th topic in the probability and stochastic processes course, in which we are going to talk about the continuous time Markov chains, or CTMCs. Continuous time Markov chain is a stochastic process in which time proceeds continuously, or the time parameter is continuous in the sense that it can be mapped to the set of real numbers. A continuous time Markov chain can be considered simply as a generalization of DTMC, in which the time proceeds in continuous manner. So instead of having, for example, in DTMC, the probability that at step x plus 1 we reside in a particular state J, where at time n the DTMC is in state I, and so forth until x1 is equal to k1, x0 is equal to k0. In CTMC, we have a continuous time. Maybe we were talking about Tn plus 1. So T is the time, the n plus first time. And this can be a real number. So at time Tn plus 1, the CTMC is in state J, where at time Tn it was in state I, at time T1 it is in state K1, and time T0 it is in K0, and so forth. So the time parameter right now is not in step, is not in something discrete, but can be continuous. If we denote this, if we show this in a timeline, then T can be anywhere. So for example, here T0 can start from time 0, T1 is somewhere between 1 and 2, as well as T2, for example, doesn't matter. T3 is between time 3 and 4, for example, Tn minus 1, Tn, Tn plus 1. So that means that the time parameter can be anywhere, and we would like to ask, for example, from the CTMC, where it resides at a particular time, let's say time Tn plus 1. And of course, this continuous time Markov chain must also satisfy the Markov, or the memoryless property, in this case, namely in the CTMC case, it can be represented as follows, namely the probability that the state at time Tn plus 1 is equal to J, given that at time Tn it is in I, at time Tn minus 1 it is in Kn minus 1, and so forth, until at time T0 it is K0. This is simply the same as the probability that it is at time Tn plus 1 is in J, and at time Tn is in I. So this is just similar to the previous one that we have seen, namely previous history before right now, before the state where we are residing right now, is not relevant to the future behavior, to the probability, or in this case to the probability that to the transition probability that we are going to take next. Therefore, a transition probability does not depend on the time already spent on a particular state, because what we are interested more is actually the time that we spent, the time between Tn and Tn plus 1. This is the time that we spent in a particular state before we do transition, before we move. So this time is basically the time spent in state I before we transition to state J. Such time, namely Tn plus 1 minus Tn, this is what we call the sojourn time, or the residence time. So therefore, the residence time or the sojourn time on a state does not influence the transition probabilities from that state to other states. And there is only one continuous probability distribution that satisfies such condition, namely the negative exponential distributions. Let's see first what is this negative exponential distribution. Let T be a random variable governed by an exponential distribution with rate lambda. So an exponential distribution is parameterized by a rate lambda, which is a positive real number. And this T, this random variable, models the sojourn time in a particular state. The probability density function of this random variable, namely the probability that the random variable t is equal to particular time t small t, is given by lambda multiplied by e to the power of minus lambda t, and its cumulative distribution function is given by 1 minus e to the power of minus lambda t. What is so special about this negative exponential distribution? It is special because restarting and rescaling it result in the original distribution. So for example, if we have a CDF, for example, as displayed or this depicted by by the figure on the left. So this is basically the curve here, the blue curve represent the cumulative distribution function, namely 1 minus e to the power of minus lambda t. Then this curve or this cumulative distribution function can be restarted at any time. For example, we decide to restart it at time t0, we stop it, and then we start it, we say that we restart again from 0, and then the curve we rescale it such that here we start from 0, and there at the end we start again approaching 1, for example, and the whole curve is rescaled. Then we obtain the original cumulative distribution function. Thereby we satisfy this condition here, namely the sojourn time, the time that we have already spent on a particular state, does not influence, does not determine the transition probability from that state to other states. This is a special property of the negative exponential distribution that makes it suitable, that makes it satisfy the Markov property. Now previously we have already mentioned that CTMC is a generalization of DTMC. We can actually move transition from DTMC to CTMC. If we have already had a DTMC, for example, let's say that the black one here is actually a DTMC. We have already seen this in our previous topic. Then we can view this DTMC as an abstract version of a CTMC, in which we are not concerned about the time, the real time that is spent in a particular state, but what we measure is just the transition. So every time it performs a transition, we say that it is a one-time unit. So the rhythm is basically the transition. Yeah. Now if we look deeper and we look at it as a CTMC, then to each state we have to associate a rate. So lambda I here is the rate of the exponential distribution governing the sojourn time in state I. So lambda I will determine how long we will stay in a particular state before we do the transition. And how do we do the transition? The transition still can be performed with the usual probability that we have before, namely decorated by b, r, 1 minus b, and so forth. So that means that we had to the DTMC we only have to add the rate of the sojourn time in every state. Now once we have that, then to each transition we will associate also the rate of that transition. The rate of this transition is simply the multiplication of the probability of that transition multiplied by the rate of the sojourn time of the originating state. So in this case, for example, the rate of this transition will be 1 minus b multiplied by lambda 1, because we start from lambda 1. For example, this one here, the rate of this transition from 2 to 3 will be equal to 1 minus r divided by lambda 2 and so forth. So we have just moved from DTMC to CTMC. If, for example, we associate to any state the rate of the sojourn time at that particular state. Like the DTMC, we also specify there are also some that we have to specify the CTMC. To specify a CTMC, we need three things. First thing is that the state space. The state space, of course, must be discrete, and we usually denote this from 1 until m. And then the second one is the initial probability distribution pi 0, where pi I0 is simply the probability that at time t0 the CTMC is at state I. And the last one is the so-called the transition rates for all possible i's and j's. Now, number 2, the initial probability distribution can be encoded by an initial probability factor. We call this factor pi 0. While number 3 can be encoded by both at the same time, a transition probability matrix together with the residence or total outgoing rate factor, namely a factor formed by the sojourn rate that we have seen before. Now, the transition probability matrix, we denote it, we have already denoted this as P, matrix P here, where basically it encodes the probability of transition from one state to another, and the residence rate factor is denoted by this factor E, which consists of lambda 1, lambda 2, and so forth until lambda n. They are the sojourn rate, the rate of the sojourn time in a particular state, in any state. Now, together, this one, the transition probability matrix, and the factor, the residence rate factor, together they form the so-called transition rate matrix, which is of the form matrix R is equal to factor E multiplied by P, matrix P. Yeah, so this basically completes. So that means that also we only need two things, namely the initial probability factor and the transition rate matrix. Like in DTMC, there are also two analysis for CTMC. The first one is the transient analysis. How do we perform a transient analysis on CTMCs? To perform a transient analysis, we first need the so-called infinitesimal generator matrix. The infinitesimal generator matrix can be obtained using this formula, namely matrix Q is equal to matrix R minus the matrix diagonal that is formed, this one, diag of factor E. This is the diagonal matrix formed by factor E. So this simply means that a matrix of the appropriate size, in which the diagonal element is formed by E, by factor E, namely lambda 1 until lambda n. Now, this infinitesimal generator matrix can be easily obtained from the rate matrix, and the difference between them is the rate tells us about the sojourn time, the parameter of the sojourn time, while here in the infinitesimal generator matrix it describes the rate of the instantaneous changes in the Markov chain. So how fast we are moving, the rate of the instantaneous changes in the Markov chain, in every state of the Markov chain. Now, the transient state probability namely the probability of being in any state, in a particular state at time t, at continuous time t, then satisfies the Kolmogorov differential equation given by this one, namely phi t dt. So this simply means that the first the first differential of factor pi t is equal to pi t multiplied by this infinitesimal generator matrix Q, with pi 0, factor pi 0 as the initial condition. So the transient analysis therefore can be expressed as the Kolmogorov differential equation. Now what is the solution of this Kolmogorov differential equation? The solution is given by this one, namely factor pi t is equal to factor pi 0 multiplied by e to the power of qt. So that means that we are doing the so-called matrix exponential. But then this operation is really difficult. Now to replace it, we are going to replace the exponent of the matrix by its power series, and the power series given by this one. So this is simply basically the power series of this exponent of the matrix. So therefore it is equal to factor pi 0 multiplied by the sum of I is equal to 0 until infinity qt to the power of I divided by I factorial. And this is what we call the transient analysis of the CTMC. But of course we will not be able to compute this up to infinity, because in that case then there won't be any n. We have to stop at some point, let's say n. This must be truncated, and this is what we call truncation point. So in the implementation we have to stop somewhere. So therefore factor pi t can be approximated by factor pi 0 multiplied by the sum of I is equal to 0 until that truncation point n, qt to the power of I divided by I factorial. The good thing about this is that if given a particular truncation point, we know actually the error of this approximation. Now the second analysis on CTMC is the steady state analysis. This is similar to the previous one that we have seen in DTMC. There are also two interpretations of this steady state analysis, namely as steady state distribution, or we can also see it as a long-term state occupancy. Recall, similarly to DTMCs, Rij is the probability of starting at state I and ending at state j at time t, at a particular time t, continuous time t. Then this steady state analysis basically boils down to compute Rijt when t is large. And the existence of these steady state probabilities is determined by this theorem, the steady state convergence theorem. And a periodic continuous time Markov chain with a single recurrent class satisfies these following three properties. The first one, for each state j, so as long as it is aperiodic and having only a single recurrent class, then for each state j, then the limit of Rijt when n, sorry, this is basically t though, where t approaches infinity is equal to pi j. And pay attention to this one, that it does not depend on I. So does not depend on the starting state. No matter where you start, then the probability of being in state j after a long time, after when t is large, or when it is already, when the CTMC is already in stationary, must be converging to some finite value, namely pi j. And this pi j is actually a unique solution of a system of linear equations given by this one, namely the sum of k is equal to 1 until m pi k multiplied by q. This is the element of the infinitesimal generator matrix. Pi kj is equal to 0. Why is it equal to 0? Because this Q basically tells us about the rate of instantaneous changes. When we are already in stationary, then actually the Markov chain is already stable. The CTMC is already stable. It is not fluctuating anymore. Yeah. So the rate of change is approaching 0 with this normalization. Therefore, we can denote this simply in terms of factor and matrix as the multiplication of factor pi multiplied by the infinitesimal generator matrix Q is equal to factor 0, where factor pi is the stationary probability distribution or the stationary probability factor. And the last one is that pi j will be equal to 0 for each transient state, and it is more than 0, a positive number, for each recurrent state. This is the end of our topic about continuous time Markov chains.